Section 7.3 in our text is constraint optimization. We're optimizing something, and then we're giving it a constraint. So constraint optimization happens a lot and I saw it a lot more in economics, but I'm sure it happens in engineering and physics and stuff like that. We're going to keep ours a little simple and just focus on just the constraints, a simple constraint, and just the quadratic forms. So we want to optimize a quadratic form, Q. We talked about Q last time. And then we want to optimize given a constraint, and the constraint is that the magnitude of the vector that we want to put in, that we want to optimize, is 1. So this kind of translates as an optimization problem that looks like this. The magnitude of your x values or your x vectors equal to 1 is just essentially the square root of x squared plus y squared is equal to 1. And so if you square both sides, then it's like saying x squared plus y squared is equal to 1. And then our quadratic form would be one of these quadratic forms where, the variables raised to the second power. So in optimizing this, one can look back to Calc 3 again and try to solve for this in a variety of different ways. Or if you don't know Calc 3, maybe you can solve for x2 and put it back into the quadratic function and have a function of just one variable and try to do it that way, which is also manageable. So I was thinking about a way to solve for this. Well, we can also look at it graphically, but let's try to solve for this and see what kind of results we're going to get using one of those methods. So let's see. You think that substitution business would work? So let's try a substitution by letting maybe solving for x2 or something in your constraint. So x2 squared is equal to 1 minus x1 squared. And since there's an x2 squared already there, let's not bother taking the square root, and let's just put this information in for x2. So our q function is actually going to equal 6x1 squared minus 4 times 1 minus x2 squared. And if we're x1 squared, thank you. And if we're solving for this, we're going to get what are we going to get? 2x1 squared minus 4. So 10 x1 squared minus 4. And then we'll solve for, let's go ahead and solve for x1. Oh, so now this q, I'm going to change the name q to little q. I don't know. So q now is a function of only one variable, and that allows us to use some calculus to solve for this. So we're going to take the derivative set equal to, is that how it goes, right? Take the derivative set equal to 0. Something like that. So let's take the derivative q prime of x1 is equal to this 20x1, and that's gone. So set that equal to 0. X is equal to 0. Ooh, x1 is equal to 0. So it looks like that attains your maximum when x1 is equal to 0. What does that mean? Oh, well, and then we should probably look for the other variable, x2 or x1. Wait, x2. So x2 squared is equal to 1 minus 0. So x2 must equal to 1. or -1? Plus or -1? Okay, so we have a couple of x, y, or x1, x2 combos that would give us some maximum or minimum. So our x1 is equal to 0, and x2 equal to 1, and x1 equal to 0, x2 equal to -1. And so we can translate these into vectors, 0, 1, 0, -1. And then when we put that into the quadratic formula, or quadratic form, we should get our values. So Q of these two vectors is going to equal to 0 in for x1, so this is -4, and the same for Q 0, -1. It looks like it might be the minimum. I think it would be 0. Yeah, so the x2 was squared, so whether it's positive or negative, it becomes positive. I suppose. But how do we know it's 1, 0? Yeah. So I think if we solve for x1 here, we're going to get 1 minus x1 squared, 1 minus x2 squared. And then we're going to go through the same thing, but it seems like we should get the other solution here. So Q is equal to 6, 1 minus x2 squared minus 4, x2 squared, and this will give us 2x2 squared -10 plus 6. So we do the derivative thing again. We're going to get, I don't know, some constant, -20 x2. And then so x2 is going to be equal to 0. And we're going to get the same kind of story here. So x2 is equal to 0. Then x1 is probably going to have to be equal to positive or -1. And then this will give us a Q of positive or -1, and 0 is equal to 6, which should be our maximum value. So these values represent the maximum value for the quadratic form, given that you're within this constraint. So if you had a Calc 3 teacher that showed you graphs and stuff, who's that? No. Actually, I taught Calc 3. Actually, I'd rather be teaching Calc 3. So if our graph is 6x squared, whoops, where am I? Probably didn't want to do that. I want to be in this 6. That's not a 6. 6x squared minus 4y squared. And then we constrain it with a circle. That's kind of hard to see. Yeah. Yeah, hold on. I'll do that. For the cases that we're going to do in this class, we're going to constrain it to just a circle. In Calc 3, you can make it whatever you want, and then you'll have to figure out. So so let's see. If we want to cut this down into just looking at the circle part, by the way, what I was trying to draw here was wherever this graph intersects the cylinder is the function that we're looking at in a constrained form. And so what we want to do is we want to find the maximum and minimum places where these two graphs intersect. Okay? Yeah, so the graph of the cylinder, it's hard to see, but technically the cylinder keeps going forever, and it just kind of stops right there for us. We can zoom out a little bit to see that it eventually would meet at some tip over here where it reaches a maximum, and some other tip down here where it has the minimum. Right. So yeah, but you don't always have the luxury of doing that if your equations are a lot more complicated. In our case, it just happened to work out that way. And in fact, after we plugged it in, it turned out nice. So anyways, the constraint is really a circle. And for us to try to visualize this a little bit better, it might be better if we actually parameterize the circle. And when we parameterize a circle, we want to parameterize it so that it's parameterized on this surface. And so there's this whole cool study in Calc 2 or Calc 3 where you get to project these curves onto the surface and find tangent vectors and tangent planes, and eventually come up with your formula for the tangent plane. So what I'm doing here is I'm replacing the z component of my parameterization with just assign and cosine, where x is equal to cosine and y is equal to sine. So I have my parameterized curve. You can't see yet unless I either make it larger or take away the graphs. Probably should be better if I go all the way up to 2 pi as well. So here is the graph that we're looking at, and the places where we hit the maximum would be those places that we're looking at. And so what did we say? We hit the maximum at 6 and -4, and so they each have their x and y components as well. So if we try to look for where those are, so the point is going to be 0, 1, and -4. And we have another point, 0, -1, and -4. So those are the two minimums from the graph. And then we try to find the maximums. It's essentially these things where you have 1, 0, and 6, and then the other one will pop up in the other graph. So that's the optimization portion of it. The constraint portion of it is restricting ourselves to the circle. And then this is a picture of that. Okay? Well, we might as well put the other one in there. So, yeah, question? No, we're just optimizing it for the sake of optimizing it. It could just be a random problem that says we have to optimize this, and this is a quadratic form. Okay, so these are, well, I can try to put some more of our graphs later, but this is the general idea behind optimization. Now, the value of 6 and -4, if you didn't already notice, happened to be the coefficients. And it turns out that this is not a coincidence. It turns out that if you have these quadratic forms that don't have any cross products, remember that's what it's called? Without those cross products, then your maximums and minimums happen at these points. Oh, well, the constraint is always going to have to be equal to 1. Yeah, because we're restricting ourselves to just that for this. Otherwise, you use Lagrange multipliers. No. Sorry. You're disappointed, I know. Oh, you'll do that in your quiz. So we have our constraint example, and let's take a look at some theorems to generalize this. So this is an example where there's no cross product terms, and so we can generalize it to find cross product terms. So we'll see that when we find cross product terms, all we're going to do is we're going to send it back to that transformation back into the no cross product terms. Remember that stuff that we did last time? So that's where we're going. So there are 3 theorems that kind of set all this up. The most important one is the last one, of course, but the first one kind of sets the stage, and the second theorem kind of gives you a first example, and then the last one puts it all together. Optimization. So it turns out that if you have a symmetric matrix, and then let's define the maximum and minimum as follows. The little m will be our minimum. And that's the minimum that you get when you do the xt, the xta, and x inverse. So remember this, or xt times a times x, not x inverse. But anyways, this is the quadratic form, right? This takes up a quadratic form if a is symmetric. And so you have a constraint, and our constraint is always going to be that unit circle, or in higher dimensions, sphere or hyperspheres or whatever you want to call it. Anyway, so we're always going to be constrained to having the magnitude of your vector to be equal to 1. And so the minimum is going to be the minimum value that you get from your quadratic form, and then the maximum would be the maximum value that you get for your quadratic form. Both of them given that you're within that constraint, that you have a unit vector. So m, the maximum value, is actually going to be your eigenvalue. It turns out to be your greatest eigenvalue. And then the minimum turns out to be your least eigenvalue. Okay, So that's the first theorem. We kind of got that. I don't know if you guys remember, but going back to the example that we just did, in this example, since there is no cross product terms, remember those eigenvalues are the coefficients. So it's 6 and -4 are the eigenvalues. So they just happen to be the coefficients. So now more generally, if you do have cross product terms, you still, if you can find the eigenvalues, which you should be able to, then those maximum and minimum values are the largest and smallest eigenvalues. Now the second theorem, yes? Yeah, that's partly, yeah. And it's also going to be important for the last section that we're doing tomorrow or Tuesday, Thursday, Wednesday. The next theorem, oh, by the way, the value itself, remember when you're finding max and mins, you have to find out what the maximum value is and where it occurs. And so the where it occurs in this case would be the vectors. So the largest eigenvalue is the maximum value, and where it occurs is that it occurs when you plug in your unit vector u1, which is the eigenvector corresponding to that particular eigenvalue. Back into the quadratic equation, when you put the u1 back into the quadratic equation or quadratic form, then you're going to get your value. So u1 is going to be the input that's going to give you lambda 1 as an output into your quadratic form. And then the minimum value corresponds to the eigenvector that's corresponding to the least eigenvalue. Okay. So Theorem 7 takes it into the next step here. It says if A, lambda 1, and u1 are exactly what's said in the theorem, which is the maximum value. A is your matrix, lambda 1 is your A is a symmetric matrix, lambda 1 is your maximum eigenvalue, and u1 is your eigenvector corresponding to that eigenvalue. Then the maximum value of this subject to the constraint, the same constraint, but now we're going to add on another constraint. And by adding on this other constraint, you're essentially taking away the largest eigenvalue already. Then the second greatest eigenvalue is going to be the new maximum. If you take away the first eigenvalue and then you redo this problem with two constraints, one of them is the original constraint, and then the other one, you take away that first eigenvalue and eigenvector. Then the next greatest eigenvalue will be your new maximum. And it corresponds to the eigenvector that's corresponding to that eigenvalue. So it's essentially putting the eigenvalues in order, and this is a way to kind of view these eigenvalues in order. So that's for two of them, and then the third theorem, Theorem 8, basically says that you can keep going with this process until you've exhausted all your eigenvalues. Okay? So that's a general idea. Okay, let's take a look at a question. No, yeah, this works for whether or not you have cross products, and it's finding it. So we didn't do an example yet of a general quadratic form with a cross product, and we'll do that in a minute. But the idea is that if you have multiple levels, if you have multiple dimensions, more than 2 dimensions usually, then you can rank your eigenvalues and your eigenvectors. Yes, you can rank your eigenvalues to be the maximum, and then another constraint, and then a maximum with a second constraint, etc. The purpose of this theorem is basically to rank your eigenvectors, eigenvalues. By ranking your eigenvalues, put them from the greatest to the smallest, then you're listing your eigenvalues, and they happen to. This is probably more of an afterthought for people. It happens to fit this particular application of optimizing with a constraint. Yeah. Yeah. No, to lambda 1. Uh, the greatest the maximum is attained when x is the eigen. Oh, so I'm sorry. This should be a 1, a 2. Thank you for pointing that out. So that's how we're going to get our. So in our really simple example with only 2 eigenvalues, and we saw the maximum and we saw the other one. So there's not much to that. All right, let's before we try a 3-dimensional problem, let's try another 2-dimensional problem. I have one kind of made up over here, where we're optimizing this thing, where it does have cross products. I should go to a new page. Let's try to optimize this given our usual constraint. So I forgot to put the constraint down. Maybe I'll write it down. Here we're just going to do equals 1 because it's only 2-dimensional. So our constraint is that x squared, x1 squared. All right, so if we're going to do this particular problem, what we need to do is we need to find eigen stuff. Yeah. Yeah. So we probably want to look at our A matrix as, you remember how to find your matrix from your quadratic form? 1 and 1, the coefficients of your squared terms, and then your middle term, your cross product term, cut in half. It's -5, -5. So let's find the eigenvalues and eigenspaces and stuff. So we have, what is it? 1 minus lambda, -5, -5, 1 minus lambda. So the determinant is 1 minus lambda squared minus 25. I think this is 1 minus 2 lambda plus. So let's start with a plus lambda squared minus 2 lambda plus 1 minus 25 lambda squared minus 2 lambda minus 24 equals 0. Lambda is equal to lambda minus 6 and positive 4. So lambda gives us 6 and negative 4. So this is our cross product terms, or this is how we get rid of our cross product terms. But these are your eigenvalues. Eigenvalues. I always get mixed up with eigenvalues and eigenvectors. So with 6 as your eigenvalue, let's figure out what the corresponding eigenvector is. So when lambda is equal to 6, we have 1 minus, so 1 minus 6. So that's -5, -5, -5, -5. So you get your v vector is going to be 1, -1. And so if we want to make this into a unit vector, 1 over root 2, negative 1 over root 2. So we have lambda is equal to negative 4. That is going to give us a positive 5. 5, negative 5, negative 5, positive 5. So our v vector is going to be 1, 1, 1 over root 2, 1 over root 2. Yes? Does it matter? I don't know. Yeah, if it's off by a scalar. So we can use v and we can use u. And we changed it by scaling. So we can scale it by a negative. It'll still be okay. It's still spanning the same space. So these are my two eigenvectors. So that means the maximum value you would get would be putting these values into, this is the larger number, right? So when you put these values back into the quadratic form, you're going to put 1 over root 2, negative 1 over root 2. So that's 1 over root 2, that's 1/2, plus they're squared, so it becomes positive, that's 1/2, minus 10 times negative 1/2, right? Because one's positive and then one's negative. So what do we have? Well, this is a positive, so that's a 5 plus 1 is 6. So theorem 8? Oh, we're not using that yet. So this is like using theorem, what's the one before that? 6. This is the one. So this is theorem 6. Well, if you have 2, technically we can use theorem 7 also. So this is our maximum, and what they're saying, if we take a look at theorem 6, we can use the same quadratic form with a constraint. Let's use the x1 squared plus x2 squared is equal to 1. And what was it? Xt, a, and u equal to 0. Let's double check. Oh, there's no a. So what we're doing here is, if we essentially eliminate this, then our maximum is capital M is equal to negative 4 with x equal to u1 or u2, which is the u2 vector. So that's what theorem 6 is, 7, 8. Theorem 7. That's what theorem 7 was saying. And we can't do theorem 8 because we only have 2 eigenvalues. It's only a 2-dimensional matrix. Yeah. Oh, because you took away the first maximum of 6. So this is like Theorem 7, step 2 kind of thing. Yeah, so if you basically eliminate your current eigenvalue, your maximum eigenvalue, then the next maximum eigenvalue is going to be -4. Yeah, you don't have to go through all that. Okay, in fact, this thing that we just did in our last step when we said check, we don't have to do that either because our theorem already said that the maximum is going to be 6, and then the maximum happens at this unit vector. The unit vector, which is the eigenvector that corresponds to that maximum value. Yeah. Yes. Oh, well, I don't want to call it rank because rank means something else. Yeah. So let's say let's say we're ordering the eigenvalues, and then eigenvalues happen to be maximums given certain constraints. Yes, correct. Yeah, yeah. The order, the sign matters. Yeah. Okay. All right. Let's do another example. So another example would be something like the something that would have 3 dimensions to it. What? Yeah. We didn't really get rid of it. We just went straight to the eigenvalue and eigenvector. Um, yeah, I mean, if we want, I could have we could have paused here and said that from here, does this look familiar? This is y1 squared times 6, and then y2 squared times -4, right? So this would have been the solution without the cross product. And then your p-value, so your d would have been 6, -4, and then your p would have been these vectors that we found. So it's minus 1 over root 2. Oops. I guess we considered it positive, right? So 1 over root 2, -1 over root 2, 1 over root 2, -1 over root 2. And the inverse of this would be to transpose. And then, so this is our diagonalization. This is our orthogonally diagonalized form. Yeah. For these problems, for the symmetric matrices. Oh, yeah. Uh-huh. Thanks, Patrick. All right. Yes. Well, this is an added constraint, and what this added constraint really does is eliminates the largest number that you have, the largest eigenvalue, and so yeah, so then the second highest value is the maximum, correct? And then if this is like a 5 by 5 matrix, then you can, I don't want to say rank, you can order the eigenvalues in this way. Yeah. No, no, no. just just the theorem. That's what theorems are for. They're to be used and abused. And if you care enough, you can prove it. All right, let's do our example. I think here we go. So now we're looking at something in 3 dimensions, or at least it'll put us in our 3. And so what we want to do is we want to start off by identifying our matrix and then finding our eigenvalues and then finding our eigenvectors. And then we would have essentially answered all the questions that would be asked in terms of optimizing this with constraints. So again, I didn't put the constraint here, but we can say the constraint is for this first one. I don't really want to call it step. It's not a step-by-step algorithm process. It's just invoking Theorem 1 and Theorem 7, 6, and 7, and 8. So let's just say first. I don't know. Let's figure out its matrix, corresponding matrix. So 5, 6, 7 in the diagonal, and so now we take a look at the cross product terms. This is a 1, 2 spot and the 2, 1 spot. So the 1, 2 spot, we got what? We got 2. So 1, 2 is 2. So this is also a 2 in the 2, 1 spot. And the 2, 3 spot. So the second row, third column, -2, and so that gives a -2 in this 3, 2 spot as well. And there's no 1, 3 spot, so we have to assume that that's 0, and so this is our matrix. This is a 3 by 3. I definitely don't want to use try to find, what do we say? Let's use Wolfram. Our eigenvalues. I think it's enough to just say eigenvalues. 5, 2, 0, 2, 6. Is that a -2? -2, 0, -2, 7. And we'll get all the information that we need. And these eigenvectors, you should double check that they are, oops, I lost one. This is coming from a symmetric matrix, so you should double check, but it should be already shown that these eigenvectors are all perpendicular or all orthogonal. Not quite yet. So what do we have to do? We have to normalize it. We have to make it into unit vectors. But if we take a look at any two of them, like the first and second one, if you dot them or you take the inner product, you're going to get 0. Let's see. You're supposed to. -2, -2, +4. That took longer. So that's 0, right? The dot products of any two vectors. So the only thing left to do is make them, if you're asked for it, to make them into unit vectors. So the unit vector in this case, U1, is going to be, is it 3? Oh, so 1/3, -2/3, 2/3. U2 is going to be 2/3, 1/3, 2/3, and then U3 is going to be -2/3, 2/3, 1/3. And so we have the corresponding, if you keep the subscripts kind of straight and focused, so we have the value for for putting this U1 into the quadratic form. All right, so what they're saying is that Theorem 6 says that the quadratic form evaluated at the vector U1 is going to be equal to 9, is the maximum. Okay. Theorem 7 says that the maximum of Qx with constraints, there's two constraints now. The first constraint is the same as the other constraint, which is x squared plus y squared plus z squared is equal to 1, or the magnitude of the vector is 1. And this is the and part. And this and part essentially eliminates the first eigenvalue out of the picture. And so what they're saying here is the next maximum is going to be the Q quadratic form evaluated at the vector U2, which, if you put this back into the original equation, you should get positive 6. And you should consider putting it back into here, except there's a bunch of fractions, so I'm not going to do it. And then Theorem 8 says that the maximum, I'll put next in parentheses, of the Q vector or the Q quadratic form with constraints. So this has your original constraint and xt u1 is equal to 0, and throw in another constraint, xt u2 is equal to 0. So this essentially gets rid of the first two maximum values, and now the next in line for the maximum is, it just happens to be that last one. Yeah. Unfortunately, nobody can see this graph because it's 3 variables, and then the maximums is in the 4th dimension. Well, it's not really much of a point for doing it for 2 dimensions. So the idea behind this process is to do it for larger dimensions, so you can shrink down, and it's basically an ordering of the eigenvalues. But it just happened to fit nicely with this idea of a constraint optimization, that this is how they presented it. Maybe it's getting you used to it, because next, like I said, in the next section they'll really want you to write it that way, because we're going to do some other decomposition that uses that. Hungry? Yeah, I know. You have everything already, right? So the only thing that this theorem is saying is that this is how you order the. This is one reason to order the eigenvalues. And that's it. Uh, yeah, usually your constraint is one dimension down. It's like essentially like finding different level curves, except like like I said, this is harder to visualize. But what you can do is you can visualize these constraints, or let's take a look at these constraints over here can kind of be visualized as level surfaces. So there's something that's happening in 3D. This one looks like it's going to be a sphere, and then this one is probably going to be a plane. And so you're looking at where there's two not intersect, but they're tangent. That's the concept, or that's the idea of Lagrange multipliers, is that they're tangent to each other, and so their gradients are collinear, parallel, whatever. Okay. Should we try to? I don't know if I want to try to visualize this. Well, the thing is that you can't visualize it. But what we could do is we can look at surfaces, and so given these two surfaces, I think we might I don't know, 15 minutes. Is this worth it? Let's see. let's let's go on a tangent. I don't know. It might help you understand it better if you took Calc 3 and you know about Lagrange multipliers, maybe. All right. All right. Well, let's try. So the magnitude of x is equal to 1. So that's in 3 dimensions. That's x squared plus y squared plus z squared is equal to 1. I don't know. Should we try to revisualize this first? Let's try to revisualize this first. Let's go back to this problem that we have over here. So remember this problem in the very beginning, and then let me actually make this a little bit thicker. No, well, let's think about that. Before it was in a cylinder, but it wasn't really on the cylinder. I mean, we can think about that cylinder. Um, well, well, okay. All right, let's the real way to assess this. I mean, looking at it in 3 dimensions is really good, but another way or a better way to reassess this is to look at different levels. And so the idea behind Lagrange multipliers is to bring this down to one level down. So instead of looking at this in 3 dimensions, let's look at it in 2 dimensions. So what I'm going to do is draw level curves. What's our function again? So z is equal to, let's put it this way, is equal to c. What's c? Come on. There you go. Can we look first? So x squared plus x squared. x squared plus y. I have to put the primes because I want to see this picture on the right side. This is your constraint. Yellow is not the best color for that. Your constraint is in blue. Okay. So what we want to do what was -4 and 6, right? So what we want to do is we want to take a look at the different levels, the level curves. In fact, we can draw the level curves. Easy to see here. If you take a look at that gray plane, that's equivalent, and that gray plane and the surface cutting each other, that's equivalent to this red curve on the right side. Okay, so the cylinder is really just a circle. So now let's slowly move this up, and at some point over here, when c is equal to, let's say -4, right? It's now tangent to each other. And I keep going, they're no longer tangent. And at another place, they become tangent to each other again. Look at the C value. C value is around 6, right? They happen to be the maximum and minimum values that we had last time. Okay? So that's the idea behind Lagrange multipliers, is that these level curves are tangent to each other. You want to go up another dimension? Let's do it. So now let's play the same game, except I'm not going to have the picture on the left side over here because it's in 4 dimensions. Whatever is happening is going to happen in 4 dimensions. So what we're going to do is we're going to take a look at the picture in 2 dimensions. No, in 3 dimensions. That has already been squashed 1 level down. So we're looking at not level curves, but level surfaces of these things. All right? So now, the function was this big mess, and then the constraint, the original constraint was lambda was x squared plus y squared plus z squared is equal to 1. So this is your original constraint. Okay, that's like the circle in our previous picture. So now let's take a look at the level surfaces. So what are some of the answers that we got? What were the max and mins values that we got? 9, 6, and 3, right? So let's go from 0 to 10 to see how this is going to change. And our function was what? 5x squared plus, was it 6? 6, it'll be y squared, right? That's x2. And then plus 7z squared for xy minus 4yz. Okay? Let's see if we can. So now we can see the inside, right? It's transparent. So now at some point over here, it touches, right? Wait. What's the A value for that one? 3. Let's keep going. And then let's keep going. Right there, right? So those are the three eigenvalues that we've got from these constraint equations. And it's totally inside. Okay? So to find the largest eigenvalue, we have somewhere over here. But now they added another constraint, right? So let's add another constraint. That other constraint was x of t. How would you write this? X t this x of x is x y z transpose. So it's x y z as a row vector dotted with -1/3, -2/3, 2/3 equal to 0. So if I multiply this out, I'm going to get a scalar function. So -1/3 x, -2/3 y, and +2/3 z. So let's take a look at that. -1/3 x, and is it another -2/3 y, and then plus 2/3 z, and this is supposed to be set equal to 0. So what happens here is that we want to eliminate their current intersection. Is this 9? Is that equal to 9 right now? Where they all touch. Where's that? Well, let's figure out where they actually touch, right? We can. What was that vector again? -1/3. -1/3 -2/3. And what was this one? Isn't that the point where they touch? Oh, it's supposed to be a point. I can't control the size of the point. So this is a point where they touch, and if we eliminate that point, then what we want to do is we're essentially eliminating that point and finding the next largest value. It's supposed to be parallel to that. So if we move that to that point, how do you move that to that point? Yeah, there's a shift, but the shift is kind of complicated. Yeah. So x plus 1/3 y plus 2/3 z minus 2/3. So that's the point that we want to eliminate, and then we're going to now look at the next largest value after getting rid of that point. And the next largest value was what we saw in that original picture already. Yeah. Okay. write your eigenvalues. Yeah. Oh, I mean, that's not what it's showing you. It's showing you that there's there's a reason. Well, yeah, I guess so. I mean, the point is that this is a solution to constrained optimization, and it just happened that the main message here is that you can just find the next maximum value by looking at the eigenvectors, which is something kind of significant. Instead of having to find the next largest, instead of finding the next instead of finding and optimizing for your next level, you just look at all the different eigenvalues. Worksheet. Oh, I think I'm gonna make it a quiz, and it's half written already. I was just debating on whether to actually give it to you in class or give it to you as a worksheet or a quiz. So I think what I'm going to do is I'm going to have you guys do it on your own at home or with other people in groups, and then count it as a quiz. I'll post it on Canvas by midnight tonight.